Okay, thanks a lot for the invitation. It's I'm very happy to talk. So I mean, this will be more of a sort of a review talk. So if you want to interrupt or ask questions, just please do not hesitate. I mean, and the point is to talk about random matrices and the model I'm going to talk about is in a sense the simplest one. So it's you pick a matrix which I will denote by U at random over the unitary group of n by n matrices, and you just pick it according to the R measure. Okay, so the R measure is in a sense, well, it's the unique measure on the group, which is left and right invariant. So what this means is that if you fix matrix V and you have your random matrix U and you multiply either to the right or to the left by V, then you get the same distribution. Okay, so it's the analog of the Lebesgue measure, you know, which is invariant by translation on R, but on the group of n by n unitary matrices. Okay, and because the matrix is unitary, what we're interested in as the eigenvalue, and they lie on the unit cycle. Okay, so the eigenvalue I will denote by exponential I theta, where this theta 1 up to theta n are the eigenangle. Maybe I can just take this pen. Are the eigenangle of the matrices. Okay, so here is a realization. So I just draw, I think, 100 by 100 matrices and plot the eigenvalue. So you see every dot is an eigenvalue on the unit cycle. So this model is called the circular unitary ensemble because the eigenvalue lie on the unit disk. And to compare with, I have drawn here independent points on the cycle. So difference you should see is that, well, the configuration of points is much more rigid for eigenvalues. So in the sense that there is no large gap or clustering phenomena like here. And in fact, this is somehow this rigidity which is interesting to understand for random matrices. You know, this has a very important consequence, you know, on the joint distribution of the eigenvalue and their fluctuations. So this is what I want to explain for this simple model here. And this is joint work with Klara Courteaut and Johansson, which are both at KTH University in Stockholm. Okay, so the point is to understand the distribution of those points, and in particular, the question I'm going to look at today and focus on is what is, so if you take the trace of U to the k for any power k, then you see this is this sum here, and I want to understand the distribution of those random variables for different k when the dimension of the matrix n tends to infinity. And as the title suggests, the answer is that there are the limiting law is Gaussian. Okay, so I want to explain this. So the first observation is that because of the invariance of the R measure, the model is invariant by translation. So you see, if you just rotate the cycle, it doesn't change the distribution of the point. So there is an invariance by rotation of this model, and this has well, first very simple consequences is that, for example, if you compute the expected value of trace of U to the k, then this is 0, just because, you know, you can multiply by an angle and this doesn't change the law, so this mean has to be 0. And similarly, these variables are uncorrelated. So if you take different k and l, this quantity is also 0. Okay. So, well, I will explain more about this, but what I want to explain is how to go deeper and, for example, compute any joint moment of this quantity or the Laplace transform to really have access to the law and show that it converges to a Gaussian as it tends to infinity. So there are many ways to do this, and there are lots of paper on the subject. So I want to review a bit what is known. So the first thing, which goes back to, in fact, Weil, is that the joint law of the eigenvalue of this R unitary matrices are known, and the formula is the following. So the joint, so this is the joint PDF of the eigenangle, is just given by this sort of product here between the pair of points and then the Lebesgue measure. Okay, so it's a simple formula, and what it means is that, okay, so there's different way to think about it. One way is you can just write this as an exponential, and then you can view this as an interacting particle system. Where you have a configuration of particle, which interact with a given energy, which is this logarithmic factor. And then this is like a Gibbs measure at a certain temperature, which is 1 in this case, and then you just sample a configuration according to this Gibbs measure, and that gives you this picture. So that's one way to think about it. So this is a Coulomb gas picture, and this has been used a lot to study this point process by Diesel, for example. Maybe a more useful way to look at it is actually to observe that there's this nice identity that if you look at this product, so Zi minus Zj, then this is just equal to a determinant. This is the determinant of the I to the j minus 1. And that's ij going from 1 to n. So this is a classical van der Monde identity. And if you use this here, you can actually just write this probability measure as determinant of some kernel. So because you get, if I put a modulo square here, I get a modulo square here, and determinant of a square is equal to determinant, of the matrix. Yeah, so this is determinant of, I guess, the sum. Yeah, it's j over k. Okay, so that's how you do the algebra, and then you find this nice formula here. And what this means is that in the language of random matrix theory, this is called the determinantal point process with a kernel Kn, which is given by this function here. So this is just a way to write this density, and this is very important because there is, you might have heard the name determinantal point process. So this is what this means is that this kernel here, it encodes all the information about the point process. So for instance, if you want to compute, so if you take a function f, right, and you compute this trace of f of u, which is just this sum over all, there's a j missing, over all possible points. So this is called the linear statistics. So for example, its expectation is just the integral of this function against the kernel. And on the diagonal, the kernel is just n, so you find n times the sort of first Fourier coefficient of f. So this is the mean, and you can do the same thing for variance. I mean, for example, here is the variance. It's given by this double integral when you have now the square of the kernel here. Okay, and same, you have formula for joint moments in general, and all correlation function or joint moment of this quantity can be computed, expressed in terms of the kernel. So this is this determinantal structure, and it's very useful. It's particularly useful for this model because the kernel is very simple. You see, it's just a sum of Fourier modes. So it's a simple object to understand. And in particular, there is a connection with Fourier analysis. You see it directly because what is this object is the kernel of the projection on L2 of of the torus, right? It's you project on the first n-1 Fourier mode, basically. Anyway, the point is, okay, so this is something you might have heard of. So I just wrote it to explain it. I'm not going to use it, but this kernel is related to the, you can rewrite it in this form. It's just summing up the series. And in particular, if you take what's called the scaling limit, so you fix a point here. Let me draw it on the picture. You fix some point theta here, and you're going to zoom in at what happened at scale 1/n. So you take this picture and you magnify it. This corresponds to doing this operation on the kernel, and you pass to the limit as n tends to infinity. then you get this object, and this is the sign kernel of random matrix theory. So what this is saying is that if I look at the point around this point theta, and I rescale them so that the distance between the typical point is of order 1, I see a universal point process, which is this sign kernel point process from random matrix theory. So this is where this sign process first appeared in the work of Dyson, and then it was shown that basically, if you have any Hermitian matrices, then this same process arises in the limit and describes the correlation of the points. Anyway, so let's go back to our original question, which is to understand what is the limiting law of this random variable, trace of UK. So, in fact, there is an old theorem which goes back to the 50s, which tell you what is the answer. So this is a random variable I'm interested in, and this object is its it is sort of Laplace transform, and there is a theorem by Gabor-Steger which says that, which gives you the asymptotic of this quantity. So it tells you that the log of this Laplace transform is equal to n f hat of 0. So remember, this is the mean. This is what we have seen, the expected value of trace of u. So it's normal, it's n times the mean plus a term. And this term is quadratic in f. So you have to think of it as being a variance. So this is a variance, and I will denote this by a of f. Okay. And then there is a vanishing error when n tends to infinity. So this convergence is nothing more than telling you that the random variable trace of f of u, it converge in distribution towards, sorry, you have to remove minus n f hat of 0 towards a Gaussian with mean 0 and variance a of f. Okay, so, and the convergence is very strong. It's a convergence in the sense of Laplace transform. So it's not only with convergence, all moments converge. And okay, and this theorem appeared in a very different context. In fact, so Steger proved the first term in 1915 and the full asymptotic in 1952. And his motivation was to study the critical easing model, where those type of questions arise as well. And there are several work which improve on Steger's original contribution. The point is that okay, many people contributed. So I won't explain how you prove this. I'll just give you a formula which is due to Borodin and Okunkov and Basser and Widom at the same time, in fact, which is called the Borodin-Okunkov formula, which explain how you obtain this result. So this formula says the following. So okay, maybe I should not have said, so h1 half means that basically this quantity is finite. So you see the f hat are always the Fourier coefficient of f, and the h1 half double f space is the space of function which are in L2, such as this quantity is finite. Okay, so it's telling you that if you take a function f where this quantity is finite, and you assume that, for example, f0 is 0, you can always remove this as a constant, then this Laplace transform is exactly equal to the following. So it's exponential of a of f. A is the variance, it's this quantity, and then there's a determinant here. So this is a Fredholm determinant. What this means is it's just a determinant of an infinite matrix. Okay, so those are matrices where where infinite matrices indexed, instead of being indexed by a finite number of entries, they are indexed by an integer. And okay, and this formula will be very important in the result I present later. So that's why I'm explaining it. So what are kf and q? So kf is some operator which depend on the function f that you choose, And you have some sort of explicit formula for it. It's very complicated, so I'm not going to write it down now. The point is it's a trace class operator. What this means is that this determinant will make sense. Okay, this is just a condition. If you don't know what trace class means. So and the important object is Qn. So what is Qn? Qn is a projection whose kernel is exactly the span of the first Fourier mode. So maybe I should have been let me be a bit more precise here. Maybe I move this down. So you see here I'm really viewing L2. You know, I'm writing it as in an orthonormal basis, which I denote by, which you can think of as being, for example, the Fourier basis. So this is well, I mean, you know, this is just okay. So this is like I denote by E1, E2 the basis of L2, and this kernel Kn that I had before, which is this CUE kernel here. This is in fact this is like you can rewrite it in the following way. So it's I don't know how to write it nicely. So well, it's like E1 star. Sorry. EJ star from J going from 0 to n minus 1. Okay, where those are the Fourier mode. So you see by a unitary transformation, I can Kn, I can think of it as being this object. And basically what this is saying is that Kn plus Qn equals the identity, right? This is what I mean by the kernel. I mean the Qn is the operator which annihilates this mode. Anyway, this is where this Qn comes from. It's identity minus Kn. And this formula is proved by, you can prove it using Fourier analysis, in fact. It's not complicated. The point is it's already give you the answer because you see Qn tends to 0 as n tends to infinity. Because Kn tends to the identity, of course. So what this is saying is that this operator here converges to 0 in the correct topology. So it's in the end you get determinant of the identity, which is 1. So it's you recover this theorem. It's telling you that this Laplace transform converges to exponential of A of f. So this is equivalent to the Sego theorem. In fact, this is stronger because this gives you an explicit error term. Okay, I'll come back to that a bit later. Okay, so I said you can prove this using Fourier analysis. There's many ways to prove it, in fact. I want to explain a connection with representation theory of the symmetric group, which is due to Diaconis and Shashahani, which explain to you, you know, the connection with, you know, why the limit is a Gaussian, basically. This is a very surprising phenomena that, you know, here you have so this trace is a sum of n random variable, right? And I just remove its mean, and I'm claiming that it converges to a non-trivial Gaussian random variable without any renormalization. So normally, if you had the classical, if the points were independent, you would need to divide by 1 over square root of n to obtain a limit. Here it's not the case. You just don't renormalize and you get a limiting Gaussian. And this is due to the, so in this picture, you would need to divide by 1 over square root of n. Here you don't. And this is due to the very strong correlation between the points. Okay, well, one way to view this, one way to prove this, another way to prove this result is with this connection with representation theory, and it's very nice, so I want to explain it. So it's due to Diaconis and Shashahani in the 80s. So it's the following. So in fact, this is I really find this theorem remarkable. So it says that if you take some numbers which are integers, non-negative, and you have a condition which is that these two sums are less than n, which is the dimension of U. Okay, so this is a condition on those sequence. The point is that okay, if this condition is satisfied, then you can compute the joint moment of the traces to some power and their conjugate. Okay, and what it's telling you is that basically, okay, this is the answer, but a good way to look at it is that this is the same as the joint moment of some other random variable, which are just IID complex Gaussian. So this theorem is telling you that if I take two sequences of number A and B, such that this sum are less than n, which is the dimension of the matrix, then the joint moments exactly match with that of the Gaussian. So it's an exact matching. It's not in the limit as n tends to infinity, it's valid for finite n. And this is extremely rare that you see, for example, if you just take j is equal to 1, for example, and no other coordinate, I mean, that's telling you that trace of U, its moment matches the one of a complex Gaussian up to order n, which is crazy. I mean, so okay, so as a simple call, we have that all those statistics converge to independent Gaussian. So, and this is another way to view this result. Okay, and you can actually use this Diaconis and Shasharani framework to be a bit more precise, and just with convergence you can actually show that in fact you have joint convergence. So if you take any number of traces up to n to the 2/3 and you compare them to Gaussian, so this is the Wasserstein one distance. Anyway, this is telling you that this joint vector, which is very large, and this vector of complex Gaussian, they have the same law as n tends to infinity. Okay, these are just some improvement of this technique. So how do you get this exact moment matching? In fact, it's due to representation theory. So the idea is to use that, we started from a matrices from the unitary group. And in fact, the character of the unitary group, there are what's called Schur polynomials, and they're indexed by integer partitions, so which are just sequence of numbers, integer which are increasing or decreasing in this case. And the Schur polynomials have this nice formula in terms of determinant. What's important is that there are symmetric polynomial in the variable theta j, which you can think of the eigenangle of the random matrices. So the point is that those are the irreducible character of UN, and in particular, they are orthonormal function with respect to this CUE measure. So this is a connection. So you see, if I take two products of those Schur polynomials for different partitions, and I compute their expectation, when I average over this CUE measure, I find 0 unless lambda is equal to mu. And there is a slight condition, which is that the dimension of the matrix needs to be bigger than the number of terms in this partition. Okay. So this, so if lambda 1 greater than lambda 2 greater than lambda L are positive, and then lambda L plus 1, etc. are all 0, then this L is the length of the partition lambda, is the number of non-zero elements. Okay. Anyway, the point is, this you know from representation theory, and the simple observation is that if you look at this quantity, which is trace of uj of aj, it's also a symmetric polynomial in this theta. It's logical because the trace are symmetric polynomial. So just when you take powers, you remain a symmetric polynomial. So you can decompose these traces in the basis of Schur polynomial. And in combinatorics, they have a name. I mean, those coefficients are known, and there are there are some some characters of a group of permutation. Anyway, it's not so important. You can write down decomposition and use this identity. And what you find is that you can compute these joint moments, and you find that it's just basically, because those are orthonormal functions, you find this sum. But those coefficients are character of a group of permutation, so they're also orthonormal. So you find this delta of mu pi, and then the normalization constant are those coefficients, which are just the moment of a complex quotient. So this is basically how Diaconis and Shashahani prove this exact matching in the, I think the article is from 91. And I mean, after that, Percy Diaconis has a question. So, okay, so you have an exact moment matching up to very high order. So you wanted to know what is the rate of convergence. So you expect that the trace of u to the j is extremely close to being a Gaussian, up to very high accuracy. And he conjectures that the rate of convergence was super exponential. So this is the result I want to present. So in fact, so the question of Diacon is what is the rate of convergence of trace of u to the k divided by square root of k to a Gaussian. And Johansson proved this result first in 98 for a fixed k basically. And the result he proved is that if you take a q to be a fixed real valued polynomial, and you define fn to be the distribution function of this random variable. So I divide by square root of a to the q to normalize it so that it has variance 1. It's centered. And he showed that you can take this distribution function, compare it to the distribution function of a standard normal, and this is in this Kolmogorov distance, and then the rate of convergence is n to the minus delta times n for a small delta. Okay, so this is indeed the conjecture of Diaconis was right. It's faster than exponential. It's to my knowledge, there is not. I mean, it's very hard to. I mean, like it's telling you that this object is closer to a normal than the precision of your computer already if n is 200 basically. I mean, because this decays like crazy. I mean, so basically, if you just sample a unitary matrices, you get Gaussian just out of those. I mean, you can get. You see, you can compute the trace and then trace square, etc., and you get k independent Gaussian with extremely high precision. So that's a way, in principle, to sample independent variable with better than computer precision. Anyway, there is another interesting phenomena. So this is what happened when this power k here is fixed. If you let k grow with n, there is a very interesting phenomena which was observed by Rains, which is the following. So what this means is that you take the spectrum of u to the m. Okay, so these are the point exponential I m theta 1 up to exponential I n theta I. Okay, so you just make in other words, if I go back to the picture, you take every point here and you make it rotate m times. This is what I'm doing here. And if you do that a large number of times, so what Rain's theorem is telling you is that the eigenvalue of these matrices are exactly, so this is an equality in distribution. They have the same distribution as the spectrum of m independent smaller matrices. Okay, so you take our distributed matrices with this dimension, which is basically n over m. There is a small correction to adjust for the missing eigenvalue, but basically, so imagine that that n is m times k, right? So what this is telling you is that you take m independent matrices, then this ni are all equal to k. So you take m independent matrices of size k by k, and you just join them spectrum. You add them together, and you recover the spectrum of the matrices rotated. So in other words, every time you make a rotation, you add a new independent matrices. So there is some independence going on when you take higher and higher power. And the corollary of Rein theorem is, for example, if you look at those points, exponential I n theta 1, exponential I n theta n, they are IID, because in this case, ni are all equals to 1. So they are just, what it's telling you is you get IID point on the unit cycle. So this is the situation is very different. If I take k to be n, now I just have a sum of independent variable, and they cannot be, in this case, the answer is that, so if you look at the rate of convergence between the distribution function of these random variables and the normal, now you have, it's of order 1 over n by the Berry essence theorem. Because the variable are independent, you cannot do better than this. So in fact, there is, for fixed k, you have an super exponential rate of convergence. This is super exponential for fixed k. Here is this. While you get polynomial for k is equal to n. And one of our goals in our paper was to understand the transition between the super exponential rate of convergence and this polynomial rate. So now let me present our results. So I will denote by f and k the probability distribution function of this random variable. So always the same one, trace of u to the k divided by square root of k. So this variable has variance 1, it's centered, and this is its PDF, okay? And I want to compare that to the PDF of a standard Gaussian in the plane. So this is the PDF of a complex Gaussian. So here Z is in the complex plane. And I want to compare these two functions. This will tell me how close are the two random variables. And our results are the following. So if you like k is equal to 1, so that means I look at the variable trace of u. So just the first traces, which is the easiest one to compute. Then our first results give you an exact asymptotic. So we now, I mean, this answers Diaconis' original question of what is the rate of convergence precisely. So the PDF of trace of u minus that of a complex Gaussian in the L2 sense converged, or it's asymptotic as n tends to infinity to a certain constant, which, okay, it's whatever it is. And then it's this, the rate is actually gamma, so this is the Euler gamma function of n plus 9/4. Okay, it's whatever that is. So the point is, you know, because it's gamma of n, it goes like actually at the leading order, it's n minus n times, you know, the correct exponential of n, etc. The Stirling approximation. So this the decay is extremely fast. I mean, and we okay. So this is asymptotics. Actually, what we are motivated by numerical application. So we wanted to say that when you take already n, which is small, you know, on a computer, if you try to sample a unitary matrices, you can. There is a nice algorithm, which basically is a QR decomposition, which allow you to sample any unitary matrices up to basically 10,000. Is very easy. But our results say that if n is just 63, so you take a very small matrices, you're already very close. I mean, so if you look at this PDF minus gamma in L1 norm, so L1 norm is very natural from a point of view in simulation because it's a total variation distance. Then you already get this gamma factor. Okay, so here there are bounds, so it's not precise asymptotic, but basically it's already exponentially small. I mean, we have effective bound already for n is 63. So this is if you want to do numerical simulation. Now, we have another result, which is what happened when k is growing. So now I'm going to assume that k is greater than 2. So I look at traces. So this is traces of u to the k divided by square root of k. Then then this is the result I was explaining. This is this interpolation between the classical CLT and the super exponential rate of convergence. So now I basically so K is allowed to grow with N, and sorry, there's a typo, so let me fix this. So it should be N divided by K, of course. So I let small n to be N divided by K. Okay, and then I still get the gamma function, but it now not in the dimension of the matrix, but in this small n parameter. So you should think of this as just being capital N divided by K. And here there is a polynomial correction, which is K to the N, okay? And so what this means is that basically you get, so if, just to be clear, if K is 1, you basically get 1 over gamma to the N plus 2 with correction, which is the super exponential rate of convergence. And if K is capital N, then you just get constant divided by n to the 1 times square root log n. Okay, so this recovers the Berry-Essen result that I presented. The square root of n here is the only, the rest is the correct answer, we believe. The square root log n is the artifact of our method. It's what we look, but besides that, yeah, it should be the correct answer. Okay. And we also have a result in the multidimensional setting. So it's a bit more complicated to state, but basically it's telling you that if you look at the joint vector now, and you compare them to Gaussian. So now I'm not comparing one random variable, I'm really comparing a Gaussian, a vector here with many components. So I can go up to square root of n, basically. And if I compare the two, then they remained exponentially close, in fact. So this n is again n over k, like before. Anyway, so these are the results we obtained. Yeah, in the last maybe 10 minutes or so I want to explain how we prove such results. First, I mean, I would like to say something is that if you look at other random matrices, you can ask the same question: what is the distribution of trace of M for another random matrix M? You will never find such answer. I mean, this super exponential rate of convergence is very special to matrices which are taken at random from classical compact groups according to the R measure. So this happened for unitary group, orthogonal group, symplectic group, and for groups of permutation. So if you take matrices uniformly at random among Sn, for example, this also works, but not for GUE or GOE. In this case, the rate of convergence are always of size 1 over n. I mean, so this is the phenomena which is related to this representation theory, if you want, or Fourier analysis. I don't know. But anyway, so how do you prove this? The proof is based on this Borodino-Kukov formula that I showed, which is a formula for the Laplace transform of the trace of f of u for a generic u in terms of a freedom determinant. So now I'm going to explain a bit more about this formula. So first part is it's just like, okay, so let me explain. I'm only going to explain how you obtain theorem 1 and 3. So theorem 1 is this asymptotic of the L2 norm between the PDF of trace of U and gamma. So there is one advantage of working with the L2 distance is that you have Plancherel theorem. So somehow the PDF minus the 1 of a Gaussian in L2 is by Fourier the same as the characteristic function, which is the Fourier transform of the PDF minus that of a Gaussian. It's very easy to Fourier transform a Gaussian. You find another Gaussian basically up to pi. Okay, and this is the characteristic function of trace of U, which you can rewrite in this way. So it's a Fourier transform of this law, and it's this, and it's of the form exactly of exponential trace of f of U, where f is this simple function. So f of exponential I theta is just I times the real part of z exponential I theta, okay? So z is my somehow demi variable here, and theta is the variable on the unit cycle. So it's just a cos, in fact. Right? If I write z as r exponential I theta, it's just cos of theta plus phi. Sorry, I should have, oops, apologies. I should have, this should be phi, of course. Yes, so it's just a cos. And in particular, you can compute this variance of this f. You find that, okay, f is as an I, so it's not really a variance anymore. There's this minus sign coming in, but then you find that it's z squared over 4. So in particular, it's the same thing as what's appearing here. So if you just apply the Borodino-Kunkov formula, you find that this quantity is just this gamma of z times this determinant. And now I will tell you what is k of f in this case. I can tell you for this case because f is a very simple function. So I can write it explicitly in this case. Okay, so this is the Borodino-Kunkov formula, and it's telling you that the L2 distance is just an integral over the complex plane of this Gaussian weight time 1 minus this determinant square. So my game will be to show that this is extremely close to 1, because if this is very close to 1, then, this cancel and I get something very small integrated against the Gaussian, so something very nice. Why is it close to 1? Is because this kf is fixed and this qn is almost 0 as a projection. So what I have to show is that kf is basically in the kernel of this operator. And the operator kf is it's classical in this business. It's a product of two uncle operators. So it's a bit hard to explain, but I just wanted to show one formula. So just to give a flavor. So kf is a product of two infinite matrices, where those matrices are uncle matrices. So for example, the H plus of a function W is a matrices where I take the Fourier coefficient of W and I put them over the anti-diagonal. So here I put W at 1, W at 2, W at 3, W at 4, W at 5, etc. So I fill in the matrix infinitely like this using the Fourier coefficient of W with the positive Fourier coefficient. And H minus is the same, but I use a negative Fourier coefficient of W. And remember, I started from a certain f here, and k of f is the following. So here, my W I choose is the exponential f minus minus f plus, and here, okay, the reciprocal. And what are f plus, f minus? Those are just the positive or negative Fourier part of the Fourier expansion of f. So, okay, so what I'm saying you is that if you give me an f, I can in principle put them in those matrices and compute kf. Of course, it's quite complicated. Now there is a very nice, the good thing is that if I am interested in traces, this f is very simple. It's just a cos function. So I can compute all its Fourier coefficient. This is very simple. And if you do that, so f is just this real part. So if you compute f plus minus f minus, you find a sign. It's not surprising. And you can compute the Fourier coefficient of the W that fill in the matrix is this integral, okay? And it turns out that, so forget about the computation. The important thing is that if you've never seen these are Bessel functions. Those are classical functions. In fact, they are Bessel function of the first kind, the I Bessel function. And in particular, we know everything about those functions. So this is something we will use in our proof that, everything is very nice. So basically what it means is that this operator kf is just a product of two matrices like this, where you fill in with Bessel function everywhere. Okay. So using this computation, you can show the following. And here you have to believe me, is that if the parameter z is small enough, and you look at this determinant, you can in fact, you see, so if you have a determinant of 1 minus a certain matrix A, which is this matrix, and it's a product of 1 minus the eigenvalue of A. Okay? And in fact, if the eigenvalue are very small, a good approximation should be that this is minus the trace of A, of course. So, you replace the 1 minus by exponential minus. So, because this is like, you see, this is just, this, oops, it's not what I wanted to do. So this is just Here's the product of exponential minus lambda j of a. Okay, so, and in fact, this is what we show. We show that this determinant up to extremely tiny errors is just exponential of minus the trace, okay? So this is the first step. And this is very simple because now we just have, instead of computing a determinant, which is complicated, now we have to compute a trace, which is much, much simpler because this operator have, they are nice. I mean, they are, yeah. So basically, if I go back, this is the quantity I wanted to compute it. I have a truncation to do, okay? But then I just get you see 1 minus that is just becoming the trace square. That's just a thing. And now I just have to compute this quantity. And I know the coefficient of those matrices, so I can easily compute the trace. And it's just matrix product. And you find that the trace of k of f times qn is just this trace. Here I just write what is k, is this product of two uncle operator. And because the operators are constant along antidiagonal, you find that it's just a sum over k of this quantity. And this is exactly equal to this sum of Bessel functions. In fact, this series, I mean, those Bessel functions, they are very nice. I mean, they have the following asymptotic expansion, for example. So it's just very simple. And what you see is that you see as k increases, you go to gamma of k, right? So and r to the k here. So this coefficient goes extremely fast to 0 as k increases. And basically what you can argue is that this sum here is governed by the first term. So at the first order, only the first term, which is k equals to 1, survive, and you find that the approximation is just this Bessel function to the power 4. And then it's just a computation. I mean, you have this integral to compute, you put the Bessel function to the power 4, then it's a saddle point computation. You just replace by the asymptotic, and in the end you get our answer. Anyway, it's just to tell you that once you have the Borodian-Konkorf formula, it's quite simple to prove the first theorem. Okay, just to finish, I want to, so this is an explanation of this result, the precise asymptotic. Of course, if you want to prove theorem 2, which is precise bound, you have to work much harder. Because now you have to, n is not large, and all those approximations I show you, you have to be very precise in the error, etc., which is where things are complicated, and even more so for theorem 4. Theorem 3 is easy to prove because we have Reihen's theorem. So let me explain just the idea behind that. So, oops, I went a bit too far. No. Yes, so it's here. So to just prove theorem 3, you use this result of Reihen that I explained, which is that the spectrum of un to the k for a fixed k is equal to the sum of the spectrum of smaller matrices, right? So what this means as the level of characteristic function, it's very nice because these are independent variables. And in particular, what this is telling you is that basically this exponential ik theta 1, this collection of random variables, so I have capital N of them, is equal in distribution to the union for j going from 0 to k minus 1 of the set exponential I theta, you put a j here, 1, so those I call nj. This is what it's telling you. So you take eigenvalues of a smaller size random matrices, you just make the union, but they are independent. So those are independent. So basically you get, this is a product. So, when you have independent guys, you become the product of the distribution. So this is what you get. And remember, I give you the asymptotic of this quantity. So we can use theorem 1, plug it in this, because now I have a 1 here, and just do the analysis, and you find theorem 3. So this is how it works. Okay, so thank you very much for listening.
Thank you, Gaultier. So let's clap our hands. Are there any comments or questions?
I see that Percy is here, actually.
I'm thrilled to be able to listen to the details. I'm glad you said something about the proof. I have a comment, which is I just find it miraculous, but from the very beginning to what you did, that is, how does it know? How, why is it so Gaussian? And
yeah, it's nobody knows.
It seems like a miracle to me, and the proofs still seem miraculous. I mean, one magical identity after another, and it just almost makes you religious. I'm not, but anyway, thanks for the hard work, and thanks for a wonderful talk is what I have to say. Thanks.
Yeah, thanks. No, yeah, I mean, yeah, this is, I think nobody knows why, I mean, that it's so Gaussian. I mean, first that it's Gaussian, it's a bit surprising, right? Because you don't renormalize. So it's not like in the independent case when you sum lots of small contribution and it gives you a Gaussian in the end. Here it's already, yeah. But so close, it's, yeah.
But even in the finite case of, the number of fixed points of a random permutation, which has a one limit theorem, it's the same kind of error, and we can prove it. It's not so hard, but why it's true?
Yeah, that's this Poisson approximation is even more surprising somehow.
It's very unsettling, and you made it more unsettling. Thank you. Good.
Let's see if there are more questions or comments. So, Gaultier, at the very beginning, you mentioned interacting particle system and temperature equal to 1, but can it be general? So, yes, so yeah, I can comment about that. Maybe it's, so sometimes people put it in blue here, a parameter beta here. Right, right. And that corresponds to put a beta here. So in fact, the usual convention is more to do it like this. This change beta to beta over 2, but then beta is equal to 2 is CUE. And for general beta, people call that the circular beta ensemble. And you see this is the, you can consider this measure for any beta, in fact. What I tell you is, so the only difference, you see, this will still be true, but now you get a slight difference, which is like you get a 2 over beta here. Okay. However, so the limit theorem is still correct in the sense of, and in fact, this paper of Johansson proved it for with this parameter beta using the Coulomb gas method. Okay. So the beta really, sorry, the beta in the limiting theorem, you see it in the variance. Yes, it's only in the variance. Okay. But not, so in the answer, it's only in the variance, but in the this particular moment matching or any rate of convergence is specific to beta is equal to 2. If you take beta being I don't know, 2.0000 whatever, it won't work. It won't be true. So in fact, you could
take beta to be 1 or 4. It's like okay again. I mean, because 1 is the orthogonal and 4 is the symplectic ensemble, and then they're beautiful formulas again. But I yes. For general beta, the errors are just, it doesn't match. Huh? Yeah, and you see, there is a bit an unsettling question is that because, okay, so the only difference is that if beta is 2, I have this nice van der Monde identity here. Okay, so in other words, if I put 2, you see I can convert the determinant of the square into a determinant of a kernel, right? This wouldn't work if I put a general beta. I mean, I cannot, you see what I mean? Or, but the point is, this starts, to make a link with lots of other things, and you can use algebraic method to prove things.
Now imagine I would take beta to be 2 plus 1 over n. It shouldn't change anything to the rate of convergence, but I have no idea to prove anything in this case because all this algebraic magic disappear, even though I am so close. I mean,
I see. And I guess
the tool, the tool for general beta are completely different. In fact, this is
Okay. See if there in this square root of log n in your interpolation theorem, it's something you cannot really get rid of.
No, it's something we cannot get rid of. It comes from from this Rein theorem somehow. It's not correct. I mean, it's just like actually it's come from. Okay, I should explain. So if you work with L2, this is fine. You can then things factorize the product and you can get asymptotics. Now, if you want to go to L1, which is the total variation distance, to go from L2 to L1, there's usually a Cauchy-Schwarz or something like that, and this is this Cauchy-Schwarz which gives you a square root log n, basically.
Okay, I see. I see. Yeah.
Oh, come on, it's not so bad. It's just a square root.
No, it's nothing. Yeah.
It's pretty good. Sorry, but
I mean, and here it's the same story. I mean, this is square root log n to the k is in the multidimensional setting is the same. It's a higher dimensional version of this. I mean.
Okay, so if there are no more questions, Gaultier, thanks again.
Yes, thank you very much.
Thank you. And we update next week for the last seminar before the break. Thank you so much.
Okay, thank you very much.
Bravo.
Bye, Gaultier.
Ciao, Klara. Oh,
Ciao.
goodbye,
Ciao.
Percy.